As I said, this chapter, one of the most difficult chapters of all chapters in the whole 1211. And I think we'll, 12 will have the same thing because you have more advanced thermodynamics based on this chapter here. So let's look at this. Now we are looking at the at the time when we have compound, we are using a pump calorimeter, which really measure the heat by exchanging its heat with H2O, correct? Water bath, and the heat is isolated, does not go out. It's contained within the calorimeter itself. So we have here ethanol, an alcohol, is combusted. It's a combustion reaction, gives us complete combustion, carbon dioxide and H2O. Now, and the heat is found to be this amount. So the heat of this combustion reaction is this amount here. The initial temperature of combustion was 24 degrees. Find its final temperature. So we did that before. So you have the Q ethanol is minus QH2O. You have two systems. One is losing heat, which is the ethanol, exothermic, and one is gaining the heat, which is H2O, endothermic. So the heat of the reaction is heat of combustion will be the mass of ethanol multiplied by its specific heat multiplied by delta T. Now, anytime you have the and this is for ethanol. So the specific ethanol, if you don't have it in your given to you, you can assume it will be close to 1 to a specific heat of H2O, because the ethanol we are using is diluted ethanol. It's not 100%. So you can fairly use the specific heat of H2O, which is this amount. 1 calorie per gram centigrade Celsius, or 4.184 joule per gram centigrade Celsius. That's the mass here. And this is T final minus T initial, correct? So T final minus T initial. So the ethanol is giving off the heat. So we are expecting that the H2O here, H2O start initial temperature 24. But since the ethanol is losing heat, so expecting the final temperature will be very high. H2O will be warmed up a little bit. That's really what's happened. When you plug in all this together here, this is from the ethanol, the heat from ethanol given off, and just transfer it into joules, multiply by 1,000. And this is the mass of ethanol, specific heat of ethanol, and this is T final minus T initial. T initial is given to you, which is here 24 here, centigrade Celsius, and then you solve it and you get T final is 37. So this is a warm up, as H2O is warmed up. So H2O is trying to warmed up. So that's the calculation of this. So let's look at another example, guys. As I said, take your time and look at all this, all those examples, and you'll see. As I said, I'm not really relying on you. That the test bank is really is the same like you have in the online stuff. Here we have another combustion reaction. You have 100 grams of the sample here. Okay, methane, natural gas, guys. Just methane here. Methane, if you put this one here, you can balance it yourself. Methane plus oxygen with the combustion reaction CO2 plus H2O. You can balance it the way it will balance the number of the whole thing. And you can see carbon is 1, hydrogen is 2, so you put 2 here. 2 is here to make the hydrogen is 4. By doing this, you have 2 oxygen, 4, then you put 2 here. So this is the balanced combustion reaction of methane. So you have 100 grams of the sample, correct, in the bomb calorimeter, and you have T final, and this is T initial, correct? And this give you the amount is coming out of this combustion. This is the amount of the energy itself. So this is the amount. So it asks you for the specific heat of methane. Well, if you look like this is given to you. It is given. This is given, because this is the final and initial, correct? And the mass is given to you, which is 100 grams. So you solve for the specific heat, correct? Just rearrange the equation. Specific heat is heat of combustion divided by the mass multiplied by delta T. So, and that's what you really get. That's what you really get. So you can see methane has larger specific heat compared with the metals. Metals, they have 0.0 something, 0.0 something in a decimal amount. So but this one here is 2.2 joules. Okay, let's take another example. All those examples, keep them available to you. You can print out those examples in front of you, see how they solve those problems. So now we have 3.12 grams of glucose. Glucose is not our sugar, but this is blood sugar. Glucose is a blood sugar. Whatever we eat at home, this is sucrose. Sucrose is between combination of glucose and it's a combination. It's disaccharide. It's not one type of sugar, but it's two molecules of sugar. Okay, guys? The ketose and aldose together. So anyway, so you have 3.12 grams of glucose. This is the formula of it. It's burned in the bomb calorimeter. Temperature is initially is this, final is this. So this is your T final. T final, correct? And this is your T initial. So it is very important to know what you have. So the calorimeter contains 0.755 grams of H2O. And the bomb itself has the heat capacity of this. This is from the heat capacity, means that the amount of the heat will be absorbed by the calorimeter, bomb calorimeter, which is contain the walls, the wiring, the thermometer, everything inside this calorimeter will absorbing heat, and is measured to be 839 joules. 839 joules. And sometimes it's very nice. The company sometimes provide this value for you, so that you know they calibrated the whole calorimeter and then tell you all this wiring inside the calorimeter, the thermometer, the two walls, and everything that's set up inside the calorimeter, absorbing, taking in heat, 839 after the combustion of the material, correct? How much heat is produced by the combustion of glucose samples? So it's asking how much is produced. Well, because the heat of this 3.112 grams glucose, correct? This heat here, after we combust the glucose, we'll get CO2 and H2O plus heat. The heat will be warming up our H2O inside the calorimeter. If you look at the calorimeter, it's like this one here. This is the calorimeter here. It has two walls just to keep the heat to leave anywhere. So it has two walls here. And here is the thermometer. And here for the wiring here. So, and the sample is here. The sample is here. So you can see, and this is has two. Sorry, it has two here because one positive. The sample will be put here. Let me just show you the sample. The sample is put here. Samples put here, and then the electrical does positive, and then this goes outside negative. And this is thermometer here, and you have stirrer. So you have thermometer and stirrer. So one thermometer, one stirrer. So you, as soon as you put the minus and the plus, you short the circuit, current will go in, and the current will ignite the sample. When the ignition is done, the whole heat will go out. Remember this outside, this one here, this is H2O here, all over the place is outside the H2O, correct? And that's the sample inside. So this is H2O here as well. That's the wall, but this H2O is outside. So when the sample is combusted, the H2O will take the heat from this combustion and it will be warmed up. The thermometer then record the temperature, correct? So now, how much heat is absorbed by the H2O? Well, it turns out to be your H2O is 775 grams, because you have to know how much you put in. That's the specific heat of H2O. This is delta T of H2O. You have the final minus initial. Final minus initial. That's given to you here. Those are the initial minus final. So this is the heat is absorbed by H2O. Now, how much heat is absorbed by the calorimeter itself? The whole wiring, the whole thermometer, the whole plus minus stirrer, all this stuff, two walls, all the stuff here is 800. Is this one here? 93 joules per centigrade Celsius. So now we want to get rid of the Celsius out. You multiply this one by delta T, you get joules. When you add this with this one here, you add those together here, you get just the amount of the heat is used to burn this glucose. It's the amount of the heat used to glucose, correct? So that's the heat. Part of it, H2O, is warmed up. Part of it, the thermometer is absorbing with all the setup of the thermometer. So this has to be kilojoule, but this is a typo. It's a kilojoule, I think. If you add them up here, it will be in kilojoule. That's the correct answer, kilojoules. So I did not see this type of setup in the past, but I don't know what will happen then in the future. They might bring it, I don't know. But usually ACS exam always concentrated itself, the final exam, on the specific heat. Put the metal inside will warm up the H2O, then give you the heat, final heat, initial heat of the metal and of H2O, and then you calculate. Okay, now we have something new here. Definition, enthalpy. Well, enthalpy is really, this is H. What is enthalpy? Well, we call it, you see here, all this is the same thing. Q, this is Q, H, and E. All these symbols here is used for heat. Leave it or not. Heat. Here. Out here, apologize. And this one here is, this one is heat. Well, you get the idea here. As soon as you touch anything, it's just taken out. So. Where is it? It's out. It looks like it's out. No, it's not out. Oh. It is here. So we said the heat. This is a heat, okay? So the heat is, as you see, all these symbols we have written before, that means heat, whether it's Q, H, whatever. So what's this unique about enthalpy? Enthalpy is just, you are considering the heat with all the internal motion of the molecules within the system itself. So heat is the sum of internal energy or internal heat plus work. This is called work. So this one is work. So if you look, that's the impact of the energy. So the energy is really what is heat. But when you look at the whole picture, U is the internal energy plus PV. PV is the pressure always constant. We don't change the pressure here. So the volume is changing. So we have this one here. So that when you have a change in enthalpy is equal to change in the internal energy and the volume. So this whole thing is work and plus the internal energy here, because it's caused by the motion of the molecules within the system itself. So this is the heat. Now, from now on, we'll not use the heat. Even if you go for 1212, this is the heat you are using. You'll be using this heat. So you'll not use any other definition of the heat except this one here. You forget for the time being for E here, although it's the same meaning, or Q. Okay, all those are heat, but you will be using just H, enthalpy, which make a lot of sense. When I say Q, I'm not considering any internal motion of the molecules or particles within the system. But I use all these is the same thing, by the way. So E, Q, H is the meaning the same thing. So, but from now on, we'll use H because it's more comprehensive. And here we have U, internal energy. What's this? Well, of the system. It's always this, you are looking at the motion of the molecules within the system itself. It's very random, and you cannot pinpoint where the motion is. It's all over the places. The molecules are all over the places. So this is your U. Then you have the work here. You look at this. So again, that's what I said for you. This is the work here, correct? Now we have to add for this, and I want to I'll show you which one you need. So look at these examples here. This is a combustion reaction, correct? This is a combustion reaction. This combustion reaction yields this amount. But remember, this is 1 mole. This is 1 mole. This is 1 mole. This is 2 moles, correct? However, if you are asked how much is 2 moles of methane will be producing, how much heat? Well, if you have this 2 here, you have to multiply everything by 2, correct? Because the balancing of a chemical equation will be changed. This is 2 and 2 and 2 and 4, correct? So this one will be, oops, sorry. This one will be 2 multiplied by this amount here. So the heat will be just 2 multiplied by the heat. So you have to watch for the whatever is asked. Here is 1 mole, but if you change it to 2 moles, then you multiply the whole equation by 2, and you multiply this one here by 2. This is for 1 mole. For 2 moles, multiply it by 2. For 3 moles, you multiply it by 3, and so on. Let's look at this. The equation will be looking differently now. Here we have 2. We have 2. We have 2. We have here what? 4. And the heat is just multiplication of this will be, here is the answer. This is very important to know. The heat will be double. So go further here, guys. Example, I have 1.5 grams of magnesium ribbon, for example, inside the lab, magnesium ribbon. I let it react with the HCl, so it gets magnesium chloride and hydrogen. This is the reaction here. You have magnesium metal reacted with HCl, concentrated HCl. You get solution of magnesium chloride, and the hydrogen will go up. Now, hydrogen, in this experiment, we ignite the hydrogen so you can hear the pop and you see the flame of hydrogen coming out. Very explosive gas. So now, we have to watch. The ratio is 1 to 2 to 1. Correct? To 1. So here, guys. 1 to 2 to 1 to 1. So this is the mole ratio. So first of all, when you say to grams are not helping us when we calculate the heat. Heat always related to what? Number of moles. So your intuition will tell you have to get rid of the grams. So you divide this one here, grams, by its atomic mass, because magnesium is an element, not molar mass, atomic mass. Atomic mass of magnesium 24. You divide it, you get this amount here. Let me take this one here. That's what you get. This number of moles coming out or used by you in the lab, correct? So this is what you have. So now you have determine the enthalpy change per mole magnesium for the reaction, and it's give you what it's giving to you. This is the reaction. What we call this reaction? What type of reaction is this? Let me take it again. Tell me what reaction is this? What type of reaction is this, guys? Don't let me down. What type of reaction is this? What type of reaction is this? Come on, guys. This type of reaction will come with you in the final exam. What type of reaction we have here? Single, yes, single displacement. Magnesium is taking over the chlorine atom, produce magnesium chloride, liberating, making hydrogen by itself orphan. So hydrogen is kicked out from HCl. So this is single. So we have to really know about this. Those are with me in the lab, the midterm. Whoever had taken already the midterm, did I put something like this? Yes. Similar to this, I put this one here in the midterm, in the lab. We have to know how to those type of reactions. It's very important because you have to know what you are dealing with. It's very, very important. What type of reaction you are dealing with. That will help you a lot. So we transfer the grams first into, let me see, maybe change the color here a little bit. That's the way, don't sleep on me here. I'll keep changing the colors here. So we divided this one here, the grams, by the atomic mass of magnesium to get number of moles. This number of moles here. But I have here, this is kilojoule. Then you divide it by the moles here, you have reduced. So those two here, this one here, divide by moles, you get the answer is kilojoule per mole. So you get this your answer by mole. And this is, when you divide those two, you get this amount here. The answer is kilojoule per mole. So now we put the thermochemical equation, and that is your thermochemical equation here. This is yours here. So you put all of them like this, and then you put your delta H. Oops, this is very important here. That's what you put. And this is just the equation itself. So put it here this way. So this is the equation here. That's the normal single replacements or displacement reaction. But with this addition here, it turns out to be thermochemical equation. So now With the negative, as I said, negative means we are dealing with exo. We are dealing with what? Exo. It's positive, dealing with endo. Okay, guys. Okay, so let me go and look the next example. Effect of temperature of enthalpy. Well, the enthalpy is related to the specific heat in two terms. You can work under constant pressure, or you can work under constant volume, either or. So for example, this is specific heat. See here, let me see. Here it is. This one here called specific heat at constant pressure. And this is the same thing here, Q. Instead of Q, what you put your delta H, correct? That's the same thing. And this is delta B. But the whole thing is under constant pressure. We have, again, I did not put this one. We have, if you go for we have CV, which is the same thing as delta H divided by delta T, final minus initial, and the whole thing is constant volume. So constant volume. So either you have the constant pressure or specific heat at constant pressure, or specific heat at constant volume. So either or you have, correct? So sometimes you say standard enthalpy. Well, what do we mean by standard enthalpy by definition? Well, we relate this one here, condition, we put to ourselves is standard conditions here. Whenever, this is most of the time, standard means it is. A pressure has to be always one, pressure is always 1 atm. 1 atm, correct? Temperature always 25 degrees. Which is 298 Kelvin, capital K. So, yeah, if you look at this, this is the standard condition. Now, this is for the heat. If you speak a solution, then you speak about heat of solution. That's heat of the reaction, heat of combustion, correct? Heat of formation. All type of heat here will come, and if we deal with, if we are dealing with the standard condition, we relate ourselves to one. There's sometimes multiple choices come in the ACS exam. What is standard condition related to this combustion reaction? Well, then give you all the conditions, so you have to watch out. It has to be, pressure has to be 1 atm, and the temperature has to be 298 Kelvin or 25 degrees Celsius, correct? Now, if you are dealing with solutions, then you speak 1 molar solution. So if I'm dealing with solutions here, that's don't worry about it. I don't think it will come. But in 1212, if you are dealing with solutions, so then you'll have to have 1 molar. So you have those two. Solution will have 3 conditions. One, pressure is 1 atm, temperature is 225 degrees or 298 Kelvin. And now, because you are dealing with solutions, solution has to be 1 molar. Solution has to be 1 molar. Those are standard conditions. Will go all in chemistry and even physics. So physics and chemistry and engineering as well. So those are the conditions we are really relate ourselves. And how we relate this by the small o on the top of delta H. If you look at that delta H, it has small type of O, means always, this means standard. Standard. That's standard enthalpy or standard heat. So standard heat means if you are dealing with combustion reaction, not solution, then 1 atmospheric pressure and then 298 Kelvin or 25 centigrade Celsius. If you are dealing with solutions, Now you add to those 1 molar. The solution has to be 1 molar. Okay, guys. So here's an example of this, and it's a little bit tricky because this time give you the combustion reaction. Look at this. Give you combustion reaction. It is that's whole combustion reaction, correct? What else is give you to you? And this is the what type of reaction is this? What type of sign we have here? This is negative. This exactly perfect. Thank you. This is an exothermic exo because you have a negative sign. That's an exo. This is a thermochemical equation. This type of reaction is called combustion reaction. Dealing with pure oxygen, you have to deal with combustion reaction. So now for this here, if you use your natural gas, which we are using at home, so if you use 1.5 liter of methane for the combustion, calculate the standard enthalpy. The standard enthalpy is the pressure is 1 and the temperature is 298 Kelvin or 25 centigrade Celsius. Is given to you the density of the methane and the molar mass of methane. So you have to use both of those values. You start with the liters, correct, of methane. Then you get the liters out of your way by multiplying this by the density. So the density of methane, liter with the liter cancels out. Then you have the grams. You need the grams out because heat always per mole, not per grams. So then you divide it by the molar mass, which is 16 grams. The grams methane with the grams methane cancels out. And here is then you have a mole. And remember we have this is divide here. Here it's divide. You divide. This is divide here. So this is divide by the number of moles. So if you look here, you will have the heat, whatever you have the heat, multiply by the heat here. So the heat is mole of the mole cancels out. Not divide here. So moles of the moles cancels out, moles of the moles cancels out. So what will happen is you watch your units canceling. Liter with the liter cancels out. Gram with the gram cancels out. Mole of the mole cancels out, and you will end up this type of value. Right, guys? So that's straightforward. It's not really difficult, but you have to know sometimes they will give you a density. So the last, we have 2 topics in this chapter. Although this is a small chapter, but because of the specificity, this chapter is the worst chapter since 2019. Yesterday, I got the data from Barton Chair. He collected the data and showed all of us. And he said the students are not doing very well in this. So we are meeting this Friday to see how we can improve this. I think the videos and more worksheets will help. So more worksheets. Videos sometimes very boring for the students. They might sleep on the video itself. But the worksheets, they keep the students aware how they calculate those. Those type of, this chapter is calculations. Nothing that much of concept, but all with calculations. So the last topic, before the last topic, is standard enthalpy of formation. Of formation of what? Of a compound or molecule, correct? So what is, I wanted to put this one here, the formula in front of you, very handy. This one has to be handy. What this means, it means the sum of the standard enthalpy of formation. That's from the tables. You don't have to memorize them. They come from the tables. This one here, correct? Standard enthalpy of formation of the products minus the sum of enthalpy of the reactants. So is this coming? Yes. How many? Every semester we have 12, 11, even they bring it for 12, believe it or not. So it's coming, this one will come. They will ask you about the heat of the reaction, and they want you to calculate the heat of the reaction. Now, you cannot calculate the heat of the reaction unless you know the formation of the heat formation of the molecules. And this is, here they are. So you can print this one out and make it handy for yourself. You have to know which one is of those molecules is solid, which one is a gas, which one is a liquid, because stability will determine the heat of formation at standard condition, 1 atmospheric pressure and 25 degrees Celsius or 298. So you have to have this one handy. Okay, guys. And the SAS exam does not give you this, give you just the value of the reactants and the products. So you need this one here handy for the molecules in a solid state or a liquid state or a gaseous state. And then give you even ions, anions, cations. Those are, again, both of those two slides of the PowerPoint has to be printed out and put it in front of you. So I'm telling you up front, if there is a question then will come, then you have them ready. So you don't have to, you cannot get out of your chair and then get, you know, your material out. So you keep this one here, just make a note for yourself. You need this and this, just keep them handy, just in case they ask you of heat of reaction, then you have to use this, those two, whether it's compounds or ions. So let's look at some of the examples here. We'll take one of this is the same thing. Let's take one of the examples here. So we have what we call the first one, what we call this one here. Let me see here. What we call this gas here. Don't worry about the two. What is this gas? What's the name of it? That's covalent compound, correct? What's the name? Nitrogen monoxide, correct. Nitrogen monoxide. Do we have NO2? Yes. Produced. So what's we call this? Nitrogen what? Dioxide. Those naming of the compounds will come because that's a must. We have to know how to name those compounds. So now we have, what type of reaction is this? What type of reaction? This type of reaction has two types. What types? Combustion reaction, correct. Why is combustion? Because you let it react with pure oxygen. Anytime you have a material, compound, or matter with oxygen, that's a combustion. That's a flame. That's a fire. That's fire is combustion. So that's a combustion reaction. But what is the most important about this? Let me take this one out. You can see it. What's unique about this? What another type, very important than combustion? What type here? Come on, guys, don't let me down. This is a combination, synthesis. Why is a combination? Because you have two molecules are combine themselves to get one single molecule. That's called combination or synthesis, correct? We have to know this. So we have to get the heat of the reaction. Well, I don't know what they are. So we have, this is gas, this is gas, this is gas. So it turns out oxygen gas, let's go here and look. Assume it's all those gas, it is. Where is oxygen? Somebody will tell me, let's see. Here. Oxygen, 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 oxygen. Somebody, that oxygen is by itself is 0, correct? So, and here we have NO2. This is for NO2. And here we have, let me take this one out. Get this carbon one. So we need this one here, correct? We need this one here. The values here. So we need this value here, and you need this value here. Those two values you need. Those two values. Oxygen, I don't see it. If you don't see it, it has to be 0 because the molecule by itself, oxygen is 0. So I don't see here any oxygen. Oh, oxygen is not there. So let me see if the other side. So here it is. Oxygen is 0. It's not mentioning any. Those are ions. All of them are ions. So let's go here and look at the value we have here. Okay, where is the, okay, we have, I think this is the question, correct? Where's the question? Here it is. So you saw the values here, correct? The 33 and the 90, and the oxygen by itself is 0. So then this is the reactant side. So here it is. This is the reactant side. This is the product side. You have to ask for the 2. So 2 of NO2, NO2 is this, multiplied by 2, correct? The beginning. 90 is reactant minus 2, multiplied by the 90 something, 90 point whatever. So this is multiplied plus the 0 from oxygen. So if you look at this, let me take it out. Here it is. That's the delta enthalpy of the reaction is equal to, here it is equal to, this is the 2 moles of NO2 is here, correct? Minus 2 moles of the NO plus O, that's oxygen. So it came up to be minus 114.14 kilojoule. So this is an exothermic reaction. So let's get into another example here. So therefore, I need this one here to know how to solve it. So writing chemical equations for delta H formation. So here it is an ether. This is a compound here. I want to see how it's formed. Well, it formed from carbon atom, oxygen molecule, and hydrogen. You just, you know, 1 oxygen, and you have 6 of hydrogen. So you have this. So this is the formation of an ether, dimethyl ether. And those are the ingredients, elements are contributing to this molecule. So we have acetone here. This is another compound, acetone. We have carbon. We have oxygen, 1 oxygen. We have 6 hydrogen. So you have this. You show you have the formation. When I say heat of formation, means you gather those elements, you combine them to produce your compound in question. Correct? So take this one out, and let's look at this. Evaluating an enthalpy of formation. Well, here it is, the same thing we did. That's another example here. This is your these are your reactants. This is your product. Go back to, it is, let me go. I go back to my table. I need HCl, I need hydrogen gas, I need chlorine gas, correct? So you have to look at all those here. Go back. Your table here, guys, and look at the chlorine gas and HCl. They should be here. They should be here, HCl. So HCl gas is here. So this is the one you need. This is the one you need, HCl gas. And then we have the HCl gas with, see, what's the example we need? See, that's your HCl. And the chlorine gas is here. You just go and look at this with the C. It goes by the alphabets, I think. The chlorine, as I said, you need this one here handy for you so you can follow the whole thing. So anyway, so if you feel that it's missing, I don't think so. It's missing. This is the most one at 1 atmospheric pressure and HCl. So you have HCl, you have chlorine and hydrogen. Hydrogen by itself is 0. When it comes to an element by itself, oxygen molecule by itself is 0. Hydrogen by itself is 0. So let's go and look. Here it is, guys. Go and look at the example here. So look at this. You have, they give you the whole thing. You don't have to calculate. They give you the whole formation. The HCl is given to you to be 92.3 kilojoules. They gave you to it. So 1 mole of hydrogen gas produces 2 moles of HCl. As you see here, let's look at this, guys, and change the color. 1 mole of hydrogen produce 2 mole of HCl, correct? So also 1 mole of chlorine, this is 1 mole, produce 2 mole of HCl. So now we have to know how much we are dealing with comes here. If both reactants and products are at standard condition, the standard enthalpy formation of HCl is 92, you have to get the how many moles. If you have 1 mole of hydrogen and 1 mole of chlorine, how much heat you are getting? Well, you put 2 moles of HCl produced. This is 2 moles. And then you have this one here per mole. So the moles with the moles will be canceling, will cancel out. And then you get just 2 multiplied by this. That's what you are getting. So last topic is, the last topic here is Hess's law. Well, the enthalpy we have so far said, what's the difference between heat, Q, and E, heat, energy, and H, enthalpy? The only difference in that, enthalpy has to take care of the internal motion of the particles within the system itself. That's the big difference. So the enthalpy is considering, that's what we are neglecting in the Q formulas or the E formulas. It takes care of the internal energy value. Now, the question is, when we say like this, we talked about the standard enthalpy at 1 pressure, 1 atm pressure, and then 25 centigrade Celsius temperature. That's for the combustion for all types of reaction. But if you are dealing with solutions, then the formation will be 1 molar. You add 1 molar. We don't have this one here, but at least later on you will see that's for solutions is 1 molar. Now, the enthalpy is said to be a state function, correct? State function. It's a state function. What means state function? A state function characterize any state function expression or like the enthalpy. The enthalpy is state function. What do we mean by state function? It means wherever I go, I get the same value. For example, let me show you what the state function is. This is the reaction A, correct? Will give me here C. That's the product. A reactants will give me C. But suppose I said, well, how about if I go multi-steps? I go here, maybe D, I go E, correct? So if I go this way here and measure the heat direct, or if I go this way here, the heat of formation does not depend on the path of the chemical reaction. So this is state function. Anytime you have state function categories or whatever, state function means this function or this formula or this expression does not depend on the path. You can take A, B, C, D, E, and then go back to C and calculate. You'll end up the same thing like in one step. Are you following me here? So state function does not depend on the amount. This is the same way when we have talked about intensive versus extensive property of the matter. Here, state function of the matter means this matter will give you amount will not depend on what type of chemical reaction, what steps of chemical reactions take. This does not change, correct? For specific chemical reaction does not change. Get the same value regardless of the path it will go, whether go A, B, C, D, and then C, or you did just one step. So extensive intensive. Intensive does not depend on the amount. It does not depend on its mass. Like the density of 1 gram of ethanol is equal to the density of million tons of ethanol. The same density does not change. So we call this one here intensive. Extensive, such as temperature, such as volume, such as specific heat, right? Those are changing. So therefore, whenever it changes, their masses will give you different values. Now, when it comes to formation, enthalpy of formation, well, it has a unique, it's not intensive or extensive function, correct? It's a property of matter, but it has a unique thing is it's remained the same. Whether you go, correct? Whether you go from one part of the reaction to the other part, correct? So the heat will not change, correct? Are you following me here? You might delay the reaction a little bit, but the heat will come out the same thing. That is the same thing if you are using your GPS from one location to the second location. And then you say to yourself, well, I will go one, telling the Google map, I don't need any highways. I don't need any ships. I don't need any intersection that have problems, maintenance. So you go from A to B, correct? And it takes a long time. You said, I changed my mind, I'll take a highway now. So what's happened? You reach the same place. The place you have reached is not changing. Are you following me here? But it might take the steps, the routes, the backdoor route, whatever you are taking. That might slow you down, whatever in the process. But at the end, you reach the same destination. Are you following me here? So this is the state function. It does not really matter whatever path you are taking. It will lead you to the same place, to the same value. Here is the value. So it does not really matter. So let's look at this example here. Let's look at this. This is the main reaction, correct? We want to get this one here. This is one way. Now you get yourself, somebody have done for you some different reactions and give you 3 routes. First, this is the product. It comes here as a reactant. Then the reactants here is here in this one with hydrogen, correct? Then the third reaction is this. Out of this here 3 values, correct? So you have to determine what's the heat of the reaction is this here, correct? Heat of formation. What is the heat coming out of this if you take it one spot, or you go for three different steps, 3 different steps. At the end, you'll end the same value, whether you make your experiment direct or you take different steps. At the end, you come up with the same thing. Let's look at the reaction here. I want you to look at this very carefully because that will come in the final exam, and I put some question in the quiz of the exam. Look at this, guys. This is what? Product. But here is reactant, correct? Let me change. Here is my product. So what should I do with this equation here? I have to flip, correct? This one I have to flip it. The first equation, I have to flip it to make sure that's the reactants on this first equation has to be product, because this is my goal here. This is my goal here. So this is my product, but here is reactant. So I have to flip the whole equation. By doing this, the value here is the same, but I have to flip the sign. So it's minus, now it's becoming what? Positive. So by doing this, the minus will turn to be positive. So let's look at this. The second one, this is reactant here, correct? And this is reactant. So I keep this one here untouched. I say myself, but I have a problem here with, this. Get this, guys. This is 2 here. And here is not 2. So I have to put this one by what? By 2. Correct? Why? Because my reactant here is 2. So then I have to multiply this value here by 2. This one remains negative. So here. This one negative because I did not change anything. I did not flip. Let's look at the third one. The third one here, hydrogen is reactant and 1 hydrogen, one mole. So it's 1 mole, 1 mole. So I keep this one here untouched. Correct? This one kept untouched. This one has to be black. So this one here will kept untouched. So now I have this one is, I have to flip it. Correct? This one I have to multiply it by 2. This one here remain as is. Correct? So now, if you look at the product minus the reactant, so the formation of this minus the sum of both, minus the sum of both. So let's look at this one here. So we have flipped the first one, changed the sign, and that's what we did here, guys. That's what we did, the positive here. And then we have to multiply this one by 2. That's came here. And this one remain as is, we did not change. Product minus the reactant. So this one will come first. That's the reactants minus, correct? And the sum of both this. So you add those up with the minus and then in front of them minus. So the answer is here, guys, will be, as you can see, that's what we did. Flip the first one, apply the second one by 2 and keep this on untouched, and you add them up and that's what you get. Remember, this is, guys, minus minus, both of them minus minus. Correct? Minus and minus plus. Minus and minus come plus, correct? So minus and minus come to plus. So those, and this is plus 226.7. Is this exothermic or endothermic? This is an endothermic. Why? It's positive. The values came out to be positive. It's an endothermic. Another reaction. Let's look at this, guys. We have this. So now what do you think? This is the product, correct? This is my product. So I keep this one here as is. I'm not changing this one here. 1 mole, 1 mole. So I'm keeping this one as is, no change when I add them up. So sulfur is not there, but oxygen is here, correct? Oxygen is 3, correct? Oxygen is 3. So what your intuition will tell you, this is already 1 here. I have to multiply this by 2, the whole equation by 2, by 2, by 2. Correct? That's another product here. So I multiply this one here by 2. Number 3, I have sulfur and carbon. However, carbon here is a reactant, and here's a reactant. So I have to flip. This one has to flip. This one I have to flip it. Why? Because I want to cancel the carbon with the carbon and sulfur with sulfur, correct? So I have to flip number 3. When I flip this one here will come to be negative 87.9. So it's negative. Everybody following what I did? So I kept the first one as is. The second one I multiplied by 2. Then the other one, flip it. So when you do the product minus the reactants, correct? So the products are, so you have here it is. Look at this products. How many you have a product? You have one of them. This is one product. This is the second product. You have 2 products here. 2 products. Oxygen is 0 by itself, always. The heat formation for oxygen by itself is a molecule 0. And then you have this one here, which is given to you as the third one. So 2 of them here together. This is double. You add them up, minus the amount here. Minus will turn out to be positive. And let me just take this one here. That's what we did. So the first one, we kept it as is. The second one, we multiplied by 2 because we have 3 oxygens. We flip the other one so we can cancel the sulfur with sulfur, correct? And carbon with carbon. So this one here with 3 oxygens, this is 1 oxygen with 3 oxygens. Oxygen is 0 minus, we have to add this one here. We have multiplied this one by 2. We add those together here. Then this one here was positive, then it will turn negative. So, and this is the value here. Again, it's endothermic reaction. This will conclude, that's still 10 minutes. So this will conclude chapter 5. Let's go for chapter 6. This at least warming up for chapter 6. So let me stop sharing, stop recording.